now I want to explain how we can reformulate this question of are there universes that have Big Bang and Big Crunch in terms of initial data. The strategy for this is the following. So we assumed our space-time to be globally hyperbolic. When it is globally hyperbolic, then there is a theorem of Bernal and Sanchez, which tells us that we can foliate this space-time into space-like Cauchy hypersurfaces. And when we do this, well, then we can produce from this Lorentzian metric a family of initial data sets. The initial data sets consist of this induced Riemannian metric on the MT slice and of the induced second fundamental form on this slice. And well, since we have these foliations, all of these slices are diffeomorphic to some fixed manifold M. So we may view this as a family of initial data sets on this fixed manifold M. Typically, well, before we said that there is this strong energy condition that is typically satisfied, which is needed for Hawking's singularity theorem. Well, there are also other energy conditions that are usually assumed to be satisfied. And one other energy condition is this dominant energy condition, which says that the Einstein curvature is positive in a certain sense or non-negative in a certain sense. The thing about this dominant energy condition is that it nicely translates into this setup of initial data sets. Namely, there are two components of this Einstein tensors that we can single out. One is the energy density, which I will call rho, and the other one is the momentum density, which I typically call J. And well, those are just obtained by inserting the unit normal on the Cauchy hypersurface into this Einstein tensor in the first slot, and then we take the normal part, which will give rho, and the tangential part will give J. Now, the nice thing about this rho and this J is they can be expressed solely in terms of this initial data sets. Namely, there are these formulas which are known as constraint equations. And the dominant energy condition, well, I said that this term here should be non-negative for all future causal V and W. And when we look at the definition of rho and J, then this implies that rho has to be larger equal than the norm of J in particular. And well, this condition that rho is larger equal than the norm of K is known as dominant energy condition for initial data sets. For technical reasons, we are going to work with a condition that is slightly stronger. That is the strict dominant energy condition. The only difference here is that we want rho to be strictly larger than the norm of J. We may ask, what does this correspond to on the other side when we are working with the space-time m bar g bar? What does this mean here? Well, and this corresponds to something that we might also call strict dominant energy condition, which is somewhat artificial, I have to admit. It means that the dominant energy condition is satisfied and the Einstein tensor is not of a specific form where, well, V is a light-like zero vector. But, well, if we assume that we have somehow a lot of different kinds of matter in our universe, and, well, maybe include some quantum effects so that the matter density, well, also of massive matter is non-zero everywhere, then this condition will also be satisfied. yeah, there's another technical thing that I will need, and this is that this Cauchy hypersurface M is compact. So we are talking about spatially compact spacetimes here. Of course, it would be nice to also generalize these results to non-compact manifolds, maybe with certain boundary conditions. But this is not what I'm going to do in this talk here. What I'm going to do is I want to define certain sets. One is the set of all initial data sets on M. So these are just pairs consisting of a metric and some 2 tensor, well, that will play the role of the second fundamental form. And on this space of initial data sets, similar to the space of all metrics, we can put some C infinity topology. And inside the space, we now singled out a subspace, namely those initial data sets that satisfy the strict dominant energy condition. And inside this subspace, we can find certain initial data sets that are special, namely those that belong or that somehow imply existence of Big Bang, and those that imply existence of Big Crunch. According to Hawking's singularity theorem, this will be the case if the norm of if the trace of K is larger than 0, then we will encounter a Big Bang. And so we call these initial data sets Big Bang initial data sets. And vice versa, if the mean curvature is negative, then we will have a Big Crunch. And so we call these Big Crunch initial data sets. Now we can reformulate our original question in terms of initial data sets. And the question is now the following. Is there a path, a continuous path inside the space of initial data sets that strictly satisfy the dominant energy condition that starts at Big Bang initial data sets and ends at Big Crunch initial data sets? So if if we have a Lorentzian manifold that has a Big Bang and a Big Crunch, both a Big Bang and a Big Crunch, then we can choose a hypersurface inside there which has a Big Bang initial data set. We can choose a hypersurface which has a Big Crunch initial data set. And then we choose a foliation between those two hypersurfaces that contain these two hypersurfaces and also consists of Cauchy hypersurfaces. And then we obtain such a path. This is somewhat the idea. So if we have a space-time which has both Big Bang and Big Crunch, then we can construct such a path in the way that I roughly along the way that I described before. And well, the idea of this project is to basically exclude existence of such paths, so that under certain conditions, we will be able to say that no such path exists. And when no such path exists, then this means that there cannot be a space-time with this Cauchy hypersurface or with a Cauchy hypersurface diffeomorphic to this specific M, which has both Big Bang and Big Crunch. Yes, so the way we're going to do this is, let's introduce some more terminology. Basically, the existence of such a path is a question about path components. inside the space of initial data sets that strictly satisfy the dominant energy condition. Namely, what you can easily check, but is a short calculation, is that all Big Bang initial data sets actually belong to the same component inside the space. And we call this component C++. And all the Big Crunch initial data sets, they will also form one component of the space, which we call C-. But the question now is, are these components the same? When there is a path from a Big Bang to a Big Crunch initial data set, then those components will be the same. And if we can somehow show that those components are not the same, we can distinguish these two components, but then there cannot be such a continuous path. So here is a little lemma that answers the question that I posed before about equality of these components under the assumption of positive scalar curvature. So when we know that M carries positive scalar curvature, then these components are actually the same. And the proof is straightforward, it's easy. You just write down the path. The path is given by, well, we take this parameter T and we map this to the pair that corresponds consists of a PSC metric in the first slot, and the second component, the second fundamental form, will be given by T times this metric. So it's just something that is purely trace, and this trace is also constant. It's constant T, this parameter. So this way we get a family of initial data sets. And then, well, there are two things to check. Firstly, you check that this connects Big Bang and Big Crunch initial data sets, so that when you insert -1, that you get a Big Bang initial data, probably a Big Crunch initial data set, and when you insert 1, then you get a Big Bang initial data set. And the other thing is you have to check that the strict dominant energy condition is satisfied. Well, and this is also an easy check, because in this case, because the second fundamental form is so easy, you get that the momentum density is 0 and the energy density is just multiple of the scalar curvature, half times the scalar curvature, so this is positive. And so the path lies completely inside this space that I called I larger than 0. So what we now found out is that when we have positive scalar curvature on M, then these two components will be the same. And the question is, well, what happens if we don't have scalar curvature? And one might think that then these components are maybe different, but that's not easy to show. Or, well, I don't know how to show this, to be honest. But what we can do is, sometimes there is a reason why there is no positive scalar curvature. Sometimes there's an obstruction for positive scalar curvature. And what I'm going to do is, I will show that when we have such an obstruction to positive scalar curvature, then, so when you have a certain obstruction to positive scalar curvature, then these components here will actually be different. So there's a first theorem that's going in that direction, or that is along these lines, which I proved a few years ago, which says that when M is compact in spin and, well, dimension larger than 2, then there's a famous obstruction to positive scalar curvature, which is that its alpha genus is non-zero. the alpha genus is non-zero, then we know that M does not carry a positive scalar curvature metric. And what I proved back then was that in this case, also these two components, C plus and C minus, are different. This is a nice theorem, but it has a little drawback, especially from the point of physics. Because when physicists talk about spacetimes, they're basically interested in the case where the spatial dimension is 3. And in spatial dimension 3, this KO group, this alpha genus lives, well, this is KO3 of -3 of the point. And well, this is 0, unfortunately. So in this case, this obstruction is never satisfied, and so we never we cannot say anything about three-dimensional manifolds using this theorem. So this is what I'm going to talk about today. This is this newer theorem that I proved in the preprint that I showed also in the first slide, which says that when M is spin and enlargeable, and I'm going to explain what enlargeable means, then these two components, C plus and C minus, are not the same. And also here, spin and enlargeable is, by a famous theorem of Gromov and Lawson, a condition that obstructs existence of positive scalar curvature. So also here we take an obstruction to positive scalar curvature and we promote it to an obstruction against connectedness of the space of initial data sets. Well, this theorem has many implications, and there are many examples for such manifolds M, which make it interesting also for applications of physicists. So one basic example of enlargeable manifolds, maybe the prototypical example, so to say, are tori. So when you have a torus, you know that it's enlargeable, and so whenever you have a space-time where the Cauchy surface is diffeomorphic to a torus, then you know that this cannot have both a Big Bang and Big Crunch. Well, more generally, when M admits a metric of negative sectional curvature, then also M is enlargeable. And then enlargeability is also a condition that is well behaved under certain constructions. So when you have two manifolds that are enlargeable, then also their product is enlargeable. Or when you have a manifold that is enlargeable and another manifold of the same dimension, then the connected sum is enlargeable again. What is especially interesting is the following three-dimensional result. When you have an oriented three-dimensional manifold, then, well, this follows from the geometrization of three manifolds, then you know that M is enlargeable if and only if M is not diffeomorphic to a connected sum of pieces that are either S1 cross S2 or quotients of the three sphere. And well, all these manifolds that I wrote down here, these direct sums, they carry positive scalar curvature metrics, and all those that are not diffeomorphic to such a thing do not carry positive scalar curvature metrics. So in this case, it's an if and only if. When we restrict to oriented three manifolds, then M is enlargeable if and only if it does not carry positive scalar curvature. So in this case, the question that I posed up here, whether there is a converse to to the statement that positive scalar curvature implies equality of the two components, this is really true. So when in the three-dimensional orientable case, when we do not have positive scalar curvature, then also these two components can be distinguished. This is the main corollary of the result that I'm talking about here, and especially in the last video, where I'm going to explain some ideas of how to prove this result.